Welcome. On this lesson, we're going to be discussing how can we create piecewise functions when the graph is being given to us. So let's get started. Looking at example 1, it says use what we have discussed in class about piecewise functions to define a piecewise function for the following given graphs. In addition, let's identify the domain, the range, and points of discontinuity. So here we have a graph which it should represent a piecewise function, and our job is to properly define a function where if we graph that function, it will give us this piecewise function. But since we have the graph, let's start by defining the domain and the range. Where we call the domain are those x values that we do have for this function. So if this is our graph, notice that we seem to be using every single x value except -4, because notice that at -4 we have a hole, and also notice that at 2 we have a hole as well. So notice that here we have some arrows that are pointing on the left, and here I have an arrow that is pointing on the right. So I know that this function is going to continue infinitely to the left and infinitely to the right. So therefore, I'm using all x values except -4 and except +2. So the way that we can define that using interval notation, that can be from -infinity. So from -infinity all the way to -4. But notice that at -4, we're not using that value. So we're going to go -4, open parenthesis, union. And we're also using those values from -4 all the way to +2. But notice that at +2, we have a hole as well. So we have to exclude that value. And also from 2 all the way to +infinity. So that's our function for the domain. Where we call the domain are all those possible x values. These are all the possible x values, everything except -4 and +2. So now for the range, that's all the y values. So let's see. What is the lowest y value that we obtain? Well, notice that the lowest y value, in this case, it is -4. Because on the left, we're going flat. So we know that the y value is neither increasing or decreasing. But then on the right, I can see that my function is just increasing. So therefore, this value of -4, that's the lowest y value that I can get. And what's the highest y value? Well, since I know that this is increasing, which notice that in this case, in here we also have a hole at 2, but this function is still going to be increasing infinitely. So therefore, somewhere in here, we're still going to use the value of 2. So therefore, the highest y value that I can obtain on this function is just +infinity. Now for discontinuity, we have either two type of discontinuity. Either we have holes or jump discontinuity, which in this case, we know that we have two discontinuities or two holes, one at -4 when x is -4, and also when x is 2. So now let's start defining this function. Now the way that we want to define our function is we're going to take a look at the graph. So here we have our graph. We want to break down this graph into little parts or little components. Well, I noticed that this graph, I can kind of cut it into 3 pieces. I can cut it into this piece right here. Also, I could have cut it into this piece right here. And also, I could have cut it into this piece right here. So notice that now what we have done here is that instead of looking at the function as a whole, I'm just going to break it down into little pieces, and I'm going to define every single piece individually. So let me just go back and let's just concentrate on this yellow section right here. Is it possible for me to define this yellow section right here? Can we come up with a function that will give us this little piece of the graph? Well, it's not that clear what it is, but notice that we can do this. Let's extend this line. If we extend this line, notice that this line, it's a representation of the function y = 2. So notice that I can see that my first section right here is just a piece or just a section of the function y = 2. Now, what's the domain, or what are the x values that we're using? Well, we're looking at the line y = 2, but we're only using those x values that are less than -4. So now this first line right here, it just represents this yellow section that we do have here. So let me just indicate that. Now let's move on to the next section. So let me just erase this here. So now let's concentrate on the next section now, because we said that we were able to cut into 3 sections. So we already defined this first section right here. So now let's define this second section right here. And let me actually just put the yellow back here so we know what we're talking about. So now, is it possible for me to define this green section right here? Well, notice that this seems to be just a linear graph. And it's a linear graph whose slope seems to be -1. And it has a y-intercept at -2. So if I extend this line, notice that this is nothing more than the function y equals -x minus 2. Because notice that this is just a line who has a y-intercept at -2 and it has a slope of -1. So that's the function. So now we have that our second section of this piecewise function, it has a function of -x minus 2. But now what are the x values that we're allowed to use? Well, we're only using those x values from -4 all the way to +2, not including -4 or +2. So we can say that x is between -4 and +2. And notice that I'm not putting an equal sign underneath those inequalities because we do have some holes at those values. So that takes care of the second section now. So if we're going to go the same way, now let's try to define this blue section. Is it possible for me to define this line? Well, notice that we don't have much information. I mean, the only thing that we know is that it's a straight line. It seems to have a slope of +1, but we need to know the y-intercept. Well, let me just erase this real quick. Using the same idea as we just did previously, we can extend this line. You notice that if we extend this line, since we already know its slope, which seems to be +1, notice that it seems to be having a y-intercept at -6. So we have a straight line whose y-intercept is -6 and its slope is 1. So therefore, this line can be seen as just x minus 6. So we have a section of the graph of x minus 6. But now notice that we're only using those x values that are greater than 2, not including 2, because remember that there's a hole here. So therefore, x is greater than 2. And what we have here on the right-hand side as f of x is the function that we were defining. So therefore, that is the piecewise function. This function that we do have here on the right-hand side, this is the function that we were looking for. So now this piecewise function, it's a representation of this graph. And the strategy here is that take a look at your graph and try to cut it into different sections and then define each section individually. And then you just put them all together and then you have your piecewise function. So now next up, I do want to discuss something very interesting, which is the idea of finding a value that will make the function continuous. So what do we mean by that? Looking at example 2, it says for the following piecewise functions, let's try to find a value of k that will make the function continuous. So even though it says here that we're going to use a QR code to confirm the results, I erased the QR code and I'm just going to direct you to the Desmos activity. Well, let's try to understand what we're doing here. It says for the following piecewise functions, we want to define a value of k that will make the function continuous. So let's pause there for a second. So when do we know that we have a function that is a continuous function? Well, a function is continuous if there is either no holes or no jump discontinuity. Or in other words, you can trace the function without lifting your pencil. There should be no holes, or there should be no jump discontinuity among them. So let's see what we have here. So here we have a function, x squared, where x is less than or equal to 5, and x plus k. And our objective is to come up with a value of k where we have either no holes or either no jump discontinuity. So how do we accomplish that? Well, let's actually visualize what's going to happen here. So let's go to our Desmos activity. So here we have our first function. Here we have the function that we're discussing. So notice that here, this red graph, it is a function of x squared, where x is less than 5, less than or equal to 5. So that's the first line of my piecewise function. And x plus k, where x is greater than 5, that's the second line of my piecewise function. So if we just notice that here we're going to change the values of k. So notice that right now, the function, it is not continuous. So let's assume that k is equivalent to 4. We can say that the piecewise function is not continuous, because notice that we have this jump discontinuity. So if we would have traced this function, we were going on red, and once we go here, we would have jumped all the way to the bottom, and then we would have continued. So that's a jump discontinuity here. So therefore, k equals 4 does not meet the requirement that we're looking for. But notice that as we increasing the value of k, the second line of my function is just getting closer and closer. So we want to find a value of k where the blue line, it literally overlaps the red. So whatever the red section ends, the blue line should continue, because that way there will be no jump and there will be no holes. But what exactly are we looking at algebraically? Well, for both lines to overlap, we're looking at where is it, at what point is x squared equals to x plus k? Because if we set them equal to each other, we know that they're going to be overlapping. But where do we want them to overlap? Well, I know that x squared is when x is less than or equal to 5. And I know that x plus k is when x is greater than 5. So I want for both functions to be equal at the value of 5, because that's where one ends and that's where the other one continues. So think about this way. If we want no holes or no gaps, we want both functions to be equivalent, so we can set them equal to each other. So we want to come up with x squared equals x plus k. So that's going to allow us to say that they're going to be equivalent. But where do we want them to be equivalent? We want them to be equivalent where one ends and the other one continue. So we want them to be equal at x equals 5. So I know that this is where it's equal to. So now let's actually substitute x equals 5. So we're going to have 5 squared equals 5 plus k. So this gives us 25 equals 5 plus k. So now k is equals to just 20. So we're saying if we let k have a value of 20, I know that both functions are going to be equal when x is 5. And that's what we wanted to do. Well, let's actually verify it. So here we have our k. Let's set k be equal to 20. Notice that at x equals 20, if we zoom in, that's exactly what we wanted, because at x equals 10, at k equals 20, the red function ends and the blue function will continue. And at this point, there will be no holes and there will be no gaps. Because notice that if we just move it a little bit, I don't know, let's put 19.8. We still have a jump discontinuity here. But if we set it exactly at 20, there it is. If we set it exactly at 20, I know that now this whole function, if I zoom out, this function is going to be continuous, because we're going to be looking at the red function, and now where the red function ends, the blue function will pick it up. So now there is no holes, there is no gaps. Therefore, the piecewise function is continuous. So let's take a look at another example here. Let's take a look at example F. We have kx to the cube, where x is less than or equal to 2, and x plus k, where x is greater than 2. And again, what do we want to do? We want to define a value for k where there is no holes or there is no jump discontinuity. So how do we get that? Well, let's look at our function. The first line is going to end at 2. And the second line is going to start at 2. So therefore, I want both functions to be equal to each other. That is guarantee for us to not have any jump discontinuity by setting them equal to each other. But notice that we want them to be equal to each other at the value of x equals 2, because the first line is going to stop at 2, and I want the second line to pick it up at 2. So all we want to do at this point, set them equal to each other and evaluate them at 2. So let's do that. So we're going to have 2 to the third equals 2 plus k. So now we're going to have k times 8 equals 2 plus k. So that's 8k equals 2 plus k. Let's solve for k. So let's subtract 1. Let's just continue it here. So now we got 7k equals to 2. So therefore, k should hold a value of 2 over 7. Well, let's see if that is true. So we're saying if we let k equals 2 over 7, then where the first function ends, the second function is going to pick it up. So there will be no holes and there will be no jump discontinuity. Well, let's see if that is true. So let's just close the first function. So now notice that here we have a decimal activity for the second function, kx cubed, where x is less than or equal to 2. That's my first line here. And x plus k, where x is greater than 2. That's my second line here. So let's plug in a value for k. And right now we're testing 2 over 7. So notice that right now, by letting k equals 20, there is this big gap right here. So we have this gap all the way from here to here. So notice that here we have this huge gap. But what if we set our k to be equals to 2 over 7? So 2 divided by 7. So if we let k equals 2 divided by 7, notice that that's exactly what we wanted. Because whatever the first line ends, we want the second line to pick it up. And notice that that's exactly the situation that we do have here. There is no holes, there is no gap, so therefore it is continuous. And with this, it ends our lesson for creating piecewise functions. But actually, before I forget, what if we change this problem to just, let's assume that this expression right here is just x is less than 2, and the second line is x is greater than 2. Now, if we still go through the same scenario, you might be tempted to say, yes, it is still 2 over 7, because that's, the algebra checks out. Set them equal to each other, plug in x equals to 2, we still get the same result. But notice that exactly at the value of 2, the first line does not use the value of 2, because we just want x is less than 2. So we're not using the value of 2 here. And the second line is not using the value of 2 here, because it's not an equal sign underneath it. So notice that if this is our situation, then the function will never be continuous, because there will always be a hole at x equals less than 2, because the value of positive 2, it's never used neither on the first line or the second line. So that's just something to understand. Don't make this just an algebraic and just a procedure problem. Understand what's going to happen here. If the first line doesn't use this 2 and the second line doesn't use this 2, and I want them to pick up at 2, they both have a hole at 2. So therefore, even if I connect them, the hole is still going to be present there. So be careful with that. Now, this ends our lesson for creating piecewise functions.